Hey everyone, welcome to another one of our deep dive videos. This week we're looking at the protein translation exercise. If you've not solved this exercise yet, your job is to take an RNA sequence, so we're in the world of genetics, an RNA sequence, and to turn it into its proteins. So we're going to give you a long sequence of letters, and those letters generally break into triplets, so 3 letters in a row. And we have a table that I'll make sure is on the screen when you're watching this video that shows the matching of those 3 letters, which we call codons, into the actual proteins that they represent. So we're going to be taking a bit of a tour. We've got, I guess, 2 fundamental ways of doing this. You've got the imperative way with looping, and then you've got a functional way that we'll look at later. But as always, there's lots of subtleties and lots of interesting things, and we do, as we like to do, also end up with assembly, just to blow your mind slightly as well. So I'm joined by Erik, as always. Erik's here to be our guiding wisdom. And Erik, let's jump straight in. And the first solution we're looking at here is NIM.
Okay, yeah. So the first version in NIM is a very imperative version. So you mentioned that we are dealing with triplets. So what we're doing in line 2, you have a count up function. It says start at 0. The maximum that you can go to is s.high, which is the index of the last character. And then each time you are iterating, increment by 3. So this will be 0, 3, 6, 9, etc. Until you reach the end. So the reason we do that, of course, because then we can just use that index, and to get the character at that index, the one after that, and the one after that, so that you have our 3 codons, our 3 codon characters. So that's what happens on line 3. You see S, and then between the curly braces, you get I ... lesser than, and then forget about the minus bit. It's just there for safety, but just read that as if it were, say, I plus 3. Which means that you get the substring of the string just of those 3 characters starting at index I. And then you can do, it's a case statement. It's similar to a switch in other languages. You can say, hey, if the value of that substring matches on line 4, for example, AUG, then we have found a codon that we have to encode as methionine. And then we do that via result.add, and the result is a value that's for the actual value that's being returned. So if you look at the function definition on line 1, you see that it returns a sequence of strings. And so result will be a sequence, and then you can add to a sequence via the add function. So that's just all quite simple. We do the same thing for other codons. The interesting bit comes at line 11, where you have 3 codons that are special. So UAA, UAG, and UGA are special in that they signify that you have to stop reading the codons. This is interpreted as stop right now, don't continue. Everything that you have up until that point is fine, but don't continue processing, even if there is more after it. And that's why we do a break, which means that we stop looping in the for loop, and we get the result being what we've already processed, but not the rest. And then just to safeguard, if there's anything that is not one of the codons that we recognize, we just raise an exception and say, hey, we didn't expect this value. But key thing is, it's a for loop. For loop is incremented by 3 each time the next iteration is done, and then you pattern match on the substring of length 3 to see which value you need to add.
Nice and simple, nice and clear. Good one to start on. Again, we mentioned this result sort of keyword in NIM in one of the previous videos. If you've not seen that before, it's quite a cool function. Rather than returning something at the end, you just have this result that is set. Its type is set in, as Erik said, in the function definition, and then you can just work with that throughout. But other than that, this looks like something you'd find, I guess, in pretty much any imperative language, Erik. Yeah, nice, simple one to start with. So moving on to another similar one, but slightly different, and that is in Go.
Yeah, so if we scroll down a bit, we see that the core logic is the same. So there is a for loop, start at 0, we stop at the length, so the final index, and we increment by 3. So this is even a bit more what people might be used to. This is not using a function, just a regular for loop. And then you get the slice. So that's again like a sub bit of the string, just those 3 characters. And then you can do stuff with it. So where this solution is different is that it separates the creating of the proteins slice or array. I think it's called a slice in Go, but many other languages call it arrays or vectors or lists even, from the individual converting of a codon to a protein. So we have a from codon function that takes in a string and it returns actually 2 values. So that's one thing that is quite common in Go, where you return multiple values. And often the case is that you return a value or you return an error. And the error will be the second value and the regular value will be the first one. And in this case, from codon returns a string, which is, well, that was the translated protein. Everything went well. But if there is an error, we can't find it, we return the second value. And we'll see how that works. So similar to the NIM solution, you can switch on the string value. And then if we find a matching case, we return the protein. But in this case, on line 16, you can see, for example, that we return methionine, nil. And that nil is the error. So that's the second value that's being returned. And it basically says, hey, everything was well. We found the right value. You don't need to do any error handling, whatever. So that's the regular case. The interesting case comes at line 29 and 30, where you have those 3 stop codons. And the value that's being returned is an empty string. Could have been basically any string, because we will ignore it anyways. But the important part is that we no longer return nil for the second, the error value, but we return error stop. And that is defined on line 7. So that's a custom error. I'm not entirely sure about using errors to do, because this is not really an exceptional case. The stop codon is something that is, well, built into the spec. So this is not exceptional, but I've seen errors being used for control flow too. So I am not a Go expert, so maybe this is absolutely fine. But I like the idea of having like this stop codon be a different thing from a regular protein. So we'll just use errors, and then in a bit we'll see how that is used. But we also have the default case, which is what basically we didn't know what to do. And then we return another error. It says error invalid base. And I like that this is now separate from the stop bit. And then we can check that in line 40 within the from RNA function. So it says from codon RNA segment. And then you can see that on the left side, you have protein, error. So, and then at the end of the line, it says error is equals nil. So that's the case where everything was fine. We found our protein, and then we just append it to the list. But if it was error stop, we stop. Basically, we return what we've already found with error being nil. So this from RNA function itself also returns 2 values. So as its first value, it returns that the protein slice, but as the second value, it will return an error. So you can see the error being returned on line 45. So the only way in which from RNA will return an error is when it was actually returning not error stop, but error invalid base. And then we just return that. And in the end, this should all work. But the key thing that makes this different from the NIM solution is that we now have explicit error handling via error values and multiple return values to sort of to work with those, which is a very Go-like thing to do.
Mm-hmm. Yeah, interesting. there's a few. It feels like there's a lot of extra little bits going on, doesn't it? I never mind like using exceptions for flow control. I know it's one of those things that wise developers shake their heads in despair at, but I often find it works really well. Yeah, I guess the only thing maybe that would be nice here would be like line 43, just having a break or something rather than duplicating line 43 and 48. But again, I think that's sort of pretty normal at the same time, isn't it?
Yeah.
So yeah, any other comments on this one, Erik?
No. I think it's fairly errs on the verbose side compared to maybe the NIM version, but it is still very clear and the error handling is explicit. So I think it's a nice solution. Yeah, I quite like it.
Okay, so next we move on to Python. This again looks at a first glance pretty similar, Erik. What's this one doing differently?
So at its core, it's doing exactly the same thing. This is basically, I would say, the other half, maybe even more, of the solution that you find in imperative languages, where there's not a function or pattern matching being used to convert the codons to the proteins, but a dictionary or a map or whatever your language calls it. I think it's called a dictionary in Python. So you can see that from line 1 to 19 is just defining a mapping from the codon to the protein. And then within the function proteins, we have the same thing. We have the for loop with the range starting from 0 and then stepped by 3. Then we do the slice thingy where we get just the codons. And then we index into the codons dictionary. So if we couldn't find anything, well, what do we do? Well, basically, we don't actually take care of that situation here. So we just ignore it. So we don't have that explicit error handling that the Go version has, but it's probably just due to the fact that the Python tests are implemented differently. So you have to assume that just these inputs will not have any errors. So you just have valid input, and it will always be a protein that you need to add to the list. So that's done in line 27. So result.append, or it is the special codon, which is encoded as stop, and then we just break, just like we did in the NIM version. So it has the same logic.
Nice.
But the key difference being that instead of having those switch/case statements, you have a map/dictionary.
Okay, cool. So that's the last of those sort of initial bundle of solutions, I guess. The next one, at first glance, the next one looks similar, but in my head it's sort of different because of the fact it uses regexes. So this is the first time we're looking at Lua in any of the videos we've recorded. So hello, Lua. Looks pretty similar, Erik, but I guess the difference starts on line 26 here.
Yeah. So it uses the dictionary that Python uses. But the thing on line 26 is that instead of using a for loop with an integer value that you increment by 3, what we do here is we're using regular expressions to get those codons of length 3. So it says RNA strand : G match, and G match is a regular expression matching. So we pass in a regular expression, and %A is stands for a character, a letter, and the syntax that the regular expression engine uses in Lua is slightly different from your regular PCRE regular expression syntax. It has a lot of similarities, but I'm almost certain that this is due to it doesn't support everything that PCRE does, because otherwise Lua would get too big and it would be bad for Lua's purpose, which is to be embedded. But let's forget about that. This is just using regular expressions to find 3 characters, and it will do that. If you just apply that to the entire string, you will get back every single codon, and then the rest is the same. So the logic is almost exactly the same. If you squint and you rename the variables, it would almost be Python code. So you get something from the map, or the table in this case, I think is the proper Lua term. And then if it is stop, you break. Otherwise, you insert it into the table. And the only thing that I found noteworthy here is that the translate codon function, it has an assert in it. In most languages, asserts are void functions, whereas they don't return any value. Just if the assertion doesn't hold, they do something, they panic or they exit or whatever. But in Lua, the nice thing about assert is that it will actually return the value if it is valid. So in this case, it says assert codon to protein with the codon as the indexer. And if that value that's being returned is nil, because it wasn't found, then the assertion will fail and it will raise the invalid codon error. But otherwise, it will just return the value. So you can return the value of the assertion. And that's actually quite nice, because otherwise you would have this single line with the assertion, then you would just return the value. So I sort of really like that about Lua.
Yeah, that's really neat. I'm trying to think if I've ever seen asserts outside of just tests before as well.
Well,
yeah, I really like that.
Lower level languages often use it.
Yeah.
So I did a bit of C++ back in the days, and using assertions was recommended. Not that I ever did it, but it was recommended. But yeah, you very rarely see it nowadays.
Yeah, and especially not in something quite high level like Lua, which is a very high level language. Cool, interesting. So moving on, we then look at something else I think this is using regexes as well, which is awk. Yeah, this is, again, seems relatively similar, Erik, but there's a lot of, especially in those first lines, a lot of syntax and bits that look a bit interesting. So talk us through this one.
Yeah, so lines 4 to 10 are setting up a dictionary, a map, so nothing really interesting there. On line 3, there's a regular expression called stop. So that's basically, that would match the stop codons, and we'll use that in a bit. But the really, really interesting part here is line 2, which has fpad in caps, and it is a built-in awk feature where you can specify the pattern for fields. So if you think about a CSV, so the pattern would be everything up until a comma, or maybe if you have a fixed width length, you would say, hey, 4 characters or whatever. But here we have 3 characters. So, but it could also be 2 or 1 if the string is not a multiple of 3. So that's why you have the dot and then the question mark after it, which is optional in regular expressions. So the regex basically says that will match either 1, 2, or 3 characters. So it's similar in the Lua case where you could, if there are 3 characters, it will match those. But if there aren't, it would also match 2 and 1. But what does the fpad thing do? Well, it will apply that regular expression to each input line and will automatically break it down into fields. And the way that you probably best illustrate this is by going down a little bit to see what the actual for loop looks like. So on line 13, you see for I equals 1, and then I is less than or greater than, less than or equal to NF, and NF is a built-in value which stands for the number of fields. So if we have a concrete example, if we have a string of length 9, we have the pattern would match 3 times, and you would have 3 fields. So NF would be 3. And $1 would be the first field, so the first 3. $2 will be the 4, 5, and 6 characters, and $3 will be 7, 8, and 9. So on line 14, you can just use dollar and then the index. So that's in this case it will be $1, $2, $3, and that will be the field value. So those codons. We don't have to do any of that slicing, that substring feature thingies that we saw previously. because that's actually built into awk, and that's a really powerful thing. So having that out of the way, on line 14, you see that we do a check whether or not the stop regex matches that field. And if it does, a very neat and nifty thing is happening. We manually set the number of fields. We're basically saying, hey, this is the the previous version of the previous field was the last thing that we found. So just stop executing, because if you say that number of fields is I minus 1, and the next time we go to that loop, it won't be I won't be less than or equal to number of fields. So it's basically a very nifty way to sort of break. But if it isn't matching stop, we just use translate, and translate is a bit down. And you take in the string, and it looks for, it uses the in keyword to see if the codon is a key in that dictionary. If so, we return its value. Otherwise, we print an error message and exit. So, but the really nifty thing here is that awk has all that that sub-slicing and looping over the fields all covered for you. And the only thing that you say, hey, this is the pattern that I'm looking for, and then you can just iterate over all those fields very easily.
Very cool. I really like the breaking into fields thing. It gives you a feel for what awk is designed for, doesn't it? And how choosing a language that's designed to do this sort of thing can just make your life so much easier. Also, the nf equals I minus 1 bit. Is there not a break in awk, or is this just someone showing off?
I think somebody's showing off. I can't imagine there not being a break, but
no, it does seem a strange thing to be missing.
But let us know if there is.
Cool, very neat. Yeah, let us know in the comments. Very neat solution. Okay, so now we move on to functional solutions, Erik.
Yeah.
And the first one we're looking at is Gleam.
So in previously we had all those for loops, but those for loops aren't really functional. So in a functional language, especially a very pure functional language like Gleam, you have to do something else, and that something else is recursion. So we see here that in the on line 3, there's a function called proteins, takes in the string. That's all well and good. But what returns is a result type. So a result type is sort of similar to this multiple return values of Go. And it will either be the thing that is after the result, the first argument, which is a list of strings. So that means everything was good. Or it is nil, and in that case, well, apparently something went wrong. We don't actually encode the error here. We could have, but this solution doesn't do that, and I guess that's how the exercise was designed. But in a production system, you might want to do something like Go, where you have result list of string or an error type. But we don't have that here, so that's fine. But to do the recursion, what we do on line 4 is we're calling toProteins, which is a helper function. It's not public, it's private. It's not exposed, and it takes in the RNA string, but it also takes a second argument, and it's called an accumulator. And it's this accumulator that is the thing that will keep track of everything that we've processed so far. So on line 4, we say, hey, toProteins RNA, and the accumulator is initially, well, the empty list, because we haven't yet done any matching. But then within the toProteins function, we pattern match on the string. We're saying, hey, if it starts with AUG, and then you have the the less than and the greater than signs, which means that concatenated with any other list. So rest is all the characters after those first 3. We're saying, hey, do a recursive call. So we're going to recursively call the function with the rest. So we basically say, hey, ignore the first 3 characters because we already processed them. But of course, we have to remember the protein that those characters map to. And that's what's being done in that accumulator value. So if you have the square brackets, Matthew9, accumulator, which basically means that, hey, this value, Matthew9 is appended is, well, prepended to the list. So it's added to the beginning of the list. And if you haven't done any functional programming, you might wonder why not at the end. And that's basically for performance reasons. So it's very common to, when you do a recursion, you prepend to an accumulator, and that's for performance. But of course, if we would do nothing at the end, you would get the reverse order, because the last item will be at the first item. And in line 23, you can see actually how you handle that. So that's the case where we've either processed a string, which means that it matches the empty string, or it's one of the 3 stop codons. And you can also see that we don't care about the rest here, because this is when we stop. We return a value. We're saying OK. So remember that result list string comma nil. This is the list string bit. And we're saying OK, which wraps it in, well, we found something. And then we do a reverse. And that's because we prepended that to that list. And we have to reverse it to get the original value. And then on line 24, that's the case where, well, we found something that we couldn't handle, and we return error, and the error value was nil. So this is a very functional way. We're doing recursion. We're building up an accumulator, and at the end, we reverse the accumulator. And this is a very common pattern. If you are afraid of the performance of having to do the reversal, don't be, because this is so common in functional language that this is highly optimized.
It's a really nice solution, isn't it? I think this is a sort of example where if you are unfamiliar with pattern matching or unfamiliar with recursion, imagine this might look a bit complicated at first glance, but actually very quickly, I think you can see how pretty the code is, like how readable the code is, and how actually just each line, just breaking it down into, okay, we've got the characters, then the rest, then we've got the recursive function with the rest, with the accumulator being added to. Like, as soon as you understand that one line of code, you basically understand recursion, you understand pattern matching. It really is as simple as just understanding that one of those single line 9, 10, 11. So yeah, hopefully if you're not so familiar with recursion, then this is something that can maybe demystify it a little bit. I know in the comments in these videos, people have said they'd like more content on recursion, more explanations on recursion. Well, hopefully this is one that you can sit with for a little bit and have a look at, and yeah, it won't be too hard. But I really like this one, Erik. I think it's
me too.
To me, it sort of feels even clearer than the looping versions. It feels really straightforward to read.
Yeah, and Gleam is a great language to show this functional approach, because it's a very pure language. It's just there's very little ceremony, I would say. Yeah,
it's a good way of putting it. Okay, so then moving on to I guess the big brother of Gleam, which is Erlang. Do you want to? This it looks very different for a functional language. Do you want to talk us through this one?
Yeah, but it is actually almost the same version as we have in Gleam. So on line from line 5 to 23, we have a map that's like the Python version. I think it's called a property list here. But the idea is that you have a dictionary-like functionality where you can have you can index with the string. So we've seen it before in different versions. And then on line 25, you see that's there's a proteins function that takes in a strand, and that's the key thing that's being called by the test. And instead of doing actual work, that function just offloads the work to a helper function. And you can see we have translate codons, we pass in the strand, and we pass in an empty list. And that's the accumulator value again. And you can see on line 28, it's actually called ACC, so accumulator. And we're doing pattern matching here. So we're saying here that if the first argument starts with X, Y, Z, the 3 values, and then the pipe means that the afterwards is the rest of the list. So T is is what in Gleam was called rest, or it's often called tail, which is why it's named T here. Then within that function, we try to get the value for the X, Y, and Z values put into its own list, And in Erlang, strings are actually lists, so that's why you can do this. And you get back 3 possible values from that prop list get value function. You either get back stop. So if you look at line 20, 21, and 22, those are the 3 stop codons, and they return a value that's called stop. It is actually an atom. So atoms are like special values. You only have one of them. Is their name is what makes them unique. And on line 30, we can pattern match on those. So we're saying, hey, if the return value of the that we get from the proteins function, proteins property list is stop, then we need to stop. So we're going to say, hey, a recursive call to translate codons with the accumulator value. And this is a choice. We could have also returned the value here, but this author wanted to have the case where this is the end. And there's a good reason for that, to be in a separate function. So on line 34, you're seeing if translate codons is called with an empty list, which means that we've reached the end of the string processing. We have the accumulator, and then we return a tuple. So we have OK, and then we do the reverse of the accumulator. And that's exactly the same pattern that we used in Gleam. Line 36 is the other case where we don't know what to do. We're just returning an error. We stop. And then on the final thing that we didn't yet discuss was on line 31, which is the undefined case, which means that nothing was found. So we could just return the error. Interestingly, this doesn't shell out to the other function, because that will be somewhat, well, you'd have to have a special value somewhere in either the first or the second argument, which is would be a bit weird. So I understand why that person is doing it this way. But then on line 32, we have this is what we hope for. Everything went well. We found a protein, and we recursively called the translate codons function with the tail, so the T, which is everything but the first 3 characters. And then we prepend the protein to the list again, prepend, so adding it to the beginning of the list. And then we just continue this recursive approach. So it's basically the Gleam solution mixed in with a little bit of the dictionary-based, for example, Python version.
Mm-hmm. Yeah, you're right. They are basically identical, aren't they? But at a glance, they looked really different. It's nice to see like the use of atoms in here. I think that's something that many people might not be so familiar with. But yeah, I think it's once you read it through, and once it's explained by someone like you, Erik, it's really neat, nice solution as well. But I think it also showcases how readable Gleam is. On the flip side of that, I guess you're a fan of the Gleam one over this, are you, or do you like this more?
Well, my natural tendency would be to Gleam, but I do quite like this one too. So I sort of like the. I don't mind the pattern matching in Gleam. Pattern matching is absolutely wonderful, but I also don't mind this property list thingy where. I think, well, it's basically sort of the same. It's like syntactic differences, but it also goes to show that many of the functional languages, once you've identified the patterns that you use in a functional language, often you can just apply them to another functional language. Because, well, if you were familiar with Gleam and you would do Erlang, you could code this up quite quickly, except for maybe doing a little Googling around syntax. But the actual implementation pattern is very similar. So,
yeah, nice. Okay, we're going to move on to a slightly different approach. This is Scala. This looks really nice to me, Erik. That's my first instinct. Is like this is great. Talk us through it, though.
I agree that it looks really, really nice, and this uses some built-in higher order functions. So not particularly a higher order function, but a built-in function called grouped will just do all that chunking up into length 3 chunks. So this is basically giving us all those 3-letter codons with just a single function call. And there are actually quite a lot of languages that have something like this. It bugged me to no end that C# didn't have this for a long time, because which meant that all my C# solution would have to do something like this manually. But I think they have something that does this right now, so that's good. But Scala had it for a long time. So then we get a sequence of those 3-letter codons. So then we need to translate them. We need to map them, which is a very common functional pattern. And in that map, we can just use pattern matching. So this is the same pattern matching that we saw in, I don't know, a Gleam or in the beginning where we did NIM. So we just have a very big case statement. And we say this: if this matches, then we return that. And the key part here is there's no error handling. So this is also a version of the exercise that doesn't require you to handle errors, but it does, of course, require you to handle the stop codons. So on line 18, 19, and 20, we just return a special stop string. And then there's a function that's called take while. And it says, hey, that underscore thingy, it means that the value that's being evaluated. So you have a sequence, and for each element in the sequence, that function that is passed into take while will be executed. And underscore stands for the value that's being passed in. So that would either be, I don't know, one of Matthew 9 or Serine or stop. And it will keep on returning the values until it reaches the stop thing, and it will disregard that one. So that's actually almost 100% what the instructions say. Keep on doing things until you've reached the stop codon. Or, of course, until you reach the end. But in that case, it will never match this and will just return everything that you have. And in the end, it's converted to a sequence back. So this is a very, very high level. I like that the take while maps so well to the instructions. So I like this solution a lot.
Yeah, this is my sort of code. I'm a big fan of this. As soon as I saw this one, I was like, why are they all not like this? This is so readable. Erik was just choking there for a second. This video is a couple of late coming out, because Erik was pretty bedridden last week with the flu that, if you watch the previous video, we saw the start of it coming. Well, this is now the aftermath of a bit of coughing, a bit of choking, but also a bit of having to look after a young child as well. So the fun of being a parent. So yeah, when I saw this, I said to Erik, the only thing I don't like about this is the fact that you've got the pairs, you've got the duplication of the proteins like multiple times and the 3 stops at the bottom. And he was like, but look at the next solution, which is mine, which doesn't do that. So Erik, show off your solution to us. This is your solution in F#.
Yeah, so this is the solution in F#. Of course, it has the proteins function definition where you take in a string and you return a list of strings. And then there's a nested function. So the do proteins function is similar to what Erlang and Gleam did, which was to have a helper function that is just there to handle that accumulator thingy like value. But in this case, we're doing it slightly differently. So if you just focus on this function, it will take an RNA string. So far, so good. And then what it returns is a tuple, a string and a string. That is similar to what we did in Go, where you return multiple values. But it is a tuple option. And an option type is the functional equivalent of null. So usually in C or C++, null is therefore to indicate the absence of a value. But in functional language, we actually encode that in the type system. So you have a separate type. It's called an option type. And if you maybe remember from the Gleam solution, we will have a result type, which is like an option type. But in the result type, you could have the error case have data. But in the option case, you don't have any data. It's either the data is there or the data isn't there. So there is no way to have additional data with the there isn't any data. It's just there isn't any data. That's it. So and then within that function, we use pattern matching. So we pattern matching on between the brackets 0.2, which is the first 3 characters. And now we do the what you like with the vertical bars. We can just chain the patterns and just have them map to the same bit of logic. And then the key thing here is that we return sum, which means that option type means we have found a value. And we're returning 2 things. So the first string is very clearly recognizable. That's the protein. So that's the value that we need to return at the end. And the second thing is the value that we need to use in the next iteration of this function. So this is almost like the recursion setup. We're just missing one thing, and that is on line 16. So there is a function called list.unfold. And this pattern of going over an input until you've reached a certain condition and then you stop, that's a very common pattern. You could do manual recursion like in Gleam or like in Erlang. But because it is such a common pattern, there is also a way to use a built-in higher order function, which is list.unfold. And that function, it will call that helper function that we pass in, do proteins, and it will keep on processing until it gets back the result value none. And none means we just stop. Everything that you've done process up until that point is fine, and you can return that. But you now need to stop. And you can see that on line 13, we have the 3 stop codons and we have the empty string. And in those cases, we say none, and we say, hey, this is a value that you don't need to be bothered with. Just stop executing, no recursion after this. And then what it will do is internally all the sum values, the very first argument to the sum values, which is methionine and leucine, it will return a list of those values. And we don't need to bother with the fact that internally it will probably prepend to a list and then reverse at the end, because that's all hidden from us. That's what the higher order function does. And I've looked at other solutions too. For example, this was also a solution that I found in Haskell. So that whole idea of there being a higher order function that's unfolding, it's there in other languages too. So this is not just F# specific. It's a thing that many functional languages will have.
And this is really nice. When I first looked at it, I actually had line 16 scrolled off the bottom of my screen. And for a moment, I was thinking, oh, this is just recursion. And then it was anyway I looked and I was like, hold on, no, there's not actually any recursion here. And then I scrolled down and was like, oh, this is interesting. So, it totally... I was going to say, it's not a different way of doing it, is it? But it's something that's handling all of that manual work for you.
We're basically offloading all the recursion shenanigans to the function.
Yeah, really nice. And another good example of, how having these strongly defined types and everything else make this sort of code possible as well. Really nice solution, Erik. Good work. So next we move, as we like to do as we get further down these videos, from the beautiful and the sane, which is what that F# solution was, to I'm going to say the less beautiful and the slightly more painful to read, and it takes a bit more effort. So I always recommend pausing and getting yourself a caffeinated beverage of your choice. I know Erik doesn't drink caffeine, but for mere mortals like me, a caffeinated beverage of choice. And we're going to look at 2 more solutions. The first one is relatively high level compared to the second one. The first one being C++. Erik.
Yeah, so when I saw this solution, I was like, why does the switch all have these weird hexadecimal values? Then I thought like, I think this might be due to C++ not allowing you to switch on non-constant values and a string being non-constant. So I'm not actually sure if modern C++ does not allow this, but I think it at least used to be the case that you couldn't switch on a string. And we saw that previously on many other languages do allow that. Many more newer languages have the ability to switch on a string. But well, it sort of makes sense because internally we're all switching on numbers even if there are strings. So why couldn't we just in quotes, convert a string to a number, and then we can actually switch on those numbers. And that's exactly what's being done here. So if you look at line 2, you get codon to integral, and it takes in as an argument, as a parameter, the string. But what it returns is an unsigned integer. So there's a loop where we just assume that the string is of length 3, and that's something that we can just assume in this case. And then there is a bit of bitwise shenanigans. You see redfall pipe equals, which is an OR. So, and then there's a bit of bit shifting to the left. And I'll leave the actual details up to the reader to fully grasp. But in essence, this is just building up 3 bytes, or basically 3 different stages. So for the first character, it's being encoded to a string. Then that value is moved to the left, and then the second value is converted to an integer, and then the third value. And in the end, you get back an integer where there is a unique number based on those 3 different ASCII characters. And then there's a set of hard-coded values. So from line 15 to 31, those are all the hard-coded number values. There's nothing different other than that it is maybe not easy to see what it maps to originally. And then the actual proteins function below it is a more regular for loop. So we start with I is 0 on line 38, and then we get all the values, we put them in a character array. So you get codons I plus 1, codons I plus 2, and then you get back the translated value from those individual character values via that whole string to integer shenanigans. So the core algorithm is the same. I'd say the only thing that is different is that there is a trick to convert strings to integers for them to be able to be used in a switch statement. Of course, this is an idiomatic C++ code. I have to say this. You could have a map like we did in Python, for example, and that will be far more idiomatic in this case. But it is a very interesting and clever solution.
2 questions. What's the emplace back bit?
That's putting something at the end of the vector. So basically push. Okay.
Second question, rather than using a switch statement, could you just use like ifs and elses with the strings instead? I presume they don't have to be constant in C++.
Absolutely, yeah.
Okay. So all of this is really just because someone wants to use switch in case.
Yeah.
Cool. Okay. So that's the C++ way. As Erik says, there might be other C++ ways.
Definitely.
We then move on to the fun of assembly. And even just glancing at the first 28 lines, I'm guessing this is a similar approach, Erik.
This is the exact same approach. So we're encoding, we don't have necessarily, we have strings in MIPS Assembly. There are, because in the end it will just be bytes basically, and we're working on the byte level usually. But line 12 to 28 is the same thing that we did previously, where we map a string of 3 characters, so 3 bytes basically, to an integer. In this case, the nice thing is that they have symbolic names, so that it could have been done in the C+ solution too. But now we can see that at least that instead of having to do 0x0 blah blah blah, we can use AUG. So that's just a name. And I find it funny that I find this MIPS version actually more readable almost than the C++ version. So, let's just continue. Then on line 32 to 38, we have the the definitions of those string values. So those will be all the bytes for that for those characters, but we can refer to them with their regular names like methionine and serine. So that's all quite good. So the actual fun bit begins in line 43, where we have our proteins function. So copy destination address on line 44. And then we can ignore the line 45. And we jump to read codon. So, of course, this will have to do something with those 3 characters. So there's a pattern here. It starts at line 62. It says, load the byte. So $A0 will be like the pointer, so the address where we're currently looking at, and the 0 before that says, give me the byte with offset 0 from that address. So it's basically the first byte. And store that in T2, which is a temporary register. So what it then does in line 63, it says if the value that we just read is 0, it means that we've reached the end of our string, because we just suppose we had just processed 3 values, or if the string is empty, the very first read will be the 0. So that's the end. So then we go to stop. Okay, suppose it was not 0, then we read on line 65. We say the same register $A0, but then offset 1. So that's the second byte. We still put that into T2 again, because we can just reuse it. We don't need the old value. And they were saying if that is 0, that means that it was just a single byte in the codon. And we can't do anything with that because we need 3. So then it jumps to invalid. Invalid is down below, and it basically will just say, hey, clear the output string, and we just stop execution. And we do the same thing with the third byte on line 68 and 69, where we're reading the offset 2. So that's the third byte from the offset $A0. If that is 0, well, incomplete codon, let's just stop. And then the fun bit begins. Then we're saying, we're using ULW, read unaligned word. And so what is a word? A byte is, well, 8 bits. A half word is 2 bytes. And a word is 4 bytes. But for our codon, we are actually only needing 3 bytes. So the trick that is being used here is that 4 bytes are being read, which is great. And we then do a bit of bitwise masking to clear the 4th byte. And that's what's being done in line 72 with AND-I and that hexadecimal number. That is clearing the 4th byte so that we only have 3 bytes in that memory value. So those are the special values that we have defined above. And what we do then is we basically have to compare it to see if it matches any of our special values. So on line 74, we're loading the value of methionine in the register T0. And then if it's equal to, if the T3 value, which is our codons, the whole trick with the word, with the clearing of the bytes, if that is equal to the value of AUG, which is once again those special values, then copy the string. And copy string will assume that the string value to copy will be in the T0 register. And in this case, that is methionine. And we'll just ignore the copy string bit because that's not really interesting. It will just output all the bytes that are in the T0, and we'll update the pointers. So if it is none of those strings, if it doesn't match AUG, then we do the same thing with phenylalanine, which is a really weird name. But it's basically the whole pattern is we load in T0 the string that we wanted to output. And then we check if it's actually, if the codon that we read, the value is matching one of the values for that protein, then we write it to the output. And then we just move to the next codon. And unless we reach one of the stop codons, and the stop codons just say, hey, we jump to the stop label. So that's on line 102 to 104. Those are the stop codons. And it will just branch to the stop label and say, hey, this is the end. So that's basically a break in our case.
Nice.
Yeah.
That's really cool. I agree. That's really readable. Like, it's a typical example of how you can look at this and see a lot of, a lot of the instructions and feel like, I don't know what BNE is. I don't know what this, I don't know what that is. But actually, when you break down and just, look through calmly, it's really straightforward and really readable. And I guess the only thing is that, as you said, copy string bit, but that's just doing some more jumps. It's not interesting, and it's also not hard.
No, it's something that you write once and then you can reuse, basically. Yeah,
that pattern of writing into a buffer that then gets conditionally used is really nice. Cool. Okay. Well, I think that's the last of them, Erik. That was an interesting little tour. Thank you very much for choosing those and putting those together. I hope if you're watching this, those have been interesting. There are lots of other solutions. We'd love to know what your favorite solution is. One of the things we've been enjoying is after these videos, people posting links to their solutions in the comments. I think YouTube tends to block links, but if you just like put your /tracks/ I don't know, Haskell /exercises/ like that bit that comes after, and it will finish with your username. If you just paste those links, those slugs, those bits of the URLs into the comments, then we can build the URLs ourselves and go and have a look at them. But we love seeing them. We love your comments. Tell us which your favorite solution was. Tell us what you could do better. That's inspired me to go and mess around with my VB1 and try pattern matching, which is newer in Ruby, which has come out recently, which I've not played with much. So I'm going to go and explore some of that afterwards. But thanks a lot, Erik, as always. Thanks for watching, everyone, and we'll see you in the next video.